next guest is a scientist at one of the premier think tanks in the country, probably the premier think tank in the country. And just for fun, he thought he'd turn his flatbed scanner into a chess opponent, and he did it. And that just shows you how much that tank's been thinking. From the PARC, formerly known as Xerox, Jeff Breidenbach, welcome. It's great to have you on the Screensavers. They don't call it Xerox PARC anymore?
No, we're PARC now.
But Xerox still owns it. It's just they spun it off, or
we've been spun out. That's right.
That's cool. Palo Alto Research Center, right?
You got it.
And what do you do at PARC? Research? Research?
I work on advanced development.
Yeah.
And that's taking some of that research and trying to make it a little more practical.
Oh, that's neat. So, in effect, that's what you've done here.
Well, what I've done here is made a fun testing tool.
Yeah.
So we try and get some of that research practical, and this makes the testing part a lot more fun.
The original research was on something called glyphs.
That's right.
What's a glyph? What is a glyph? How can you define that?
Data glyph is a really fancy way for computers to talk to other computers when the intermedium is paper, as opposed to radio or fiber optic or other communications
Now,
channel.
why would you use paper for a computer to talk to a computer?
Because sometimes the paper also is seen by a human. So it's the human being that is dominating the intermediate.
We're being nice to people.
Want to be nice to people.
Well, I could think of a check, for instance, has to be computer readable. Barcodes are, isn't that the same thing as a glyph? A barcode, is that kind of the same thing?
A data glyph is a very fancy barcode.
Okay. So it's a way for us to store information on a piece of paper that a computer can read accurately.
That's right.
Now, are these data glyphs very accurate?
We always get our message, we always get the message accurately out.
I'm going to show, this is actually on your webpage, which is parc.com, PARC.com. This is a data glyph right here, right?
That's right.
How is the data conveyed in a data glyph?
You can see these small slash marks that go forwards and backwards.
Yeah.
You can think of them as binary ones and zeros.
So which is a 1?
The 1 is going to the left.
So
Backslash.
A backslash is 1 and a slash is 0.
Yes.
Got it. Now, why use slashes instead of, say, as in barcodes, thick and wide bars?
It has to do with the human visual system. When we evolved, we looked at things like trees or the landscape.
Right.
And these things are vertical and horizontal. We're very good at picking them out.
So we're good at resolving that.
Yeah, pick them out really easily. But
Right.
things that are diagonal, we're not so good at noticing the diagonal. So if you use a lot of diagonal marks, it's a lot more unintrusive to the human eye.
Isn't that interesting? How did you find out that we don't notice slashes very well?
The visual researchers did a lot of
That's
experiments.
really cool. Well, and by doing it in slashes, you can hide information in things like pictures. Here's a picture of a girl. Now, if I hover over it, it looks like a normal picture, but that's an actual data glyph. Is it the computer ignores the thickness of the slash? It's just looking at the slash? Is that why you can do contrast and things like that?
That's exactly right.
Okay. And you can even do color. I know you have a map here where we take the color of the map. And again, the computer's just ignoring the color.
Right.
That's for human.
It's just for the human being.
Purposes. Well, so this is a demonstration of how a computer, a PC in this case, and a scanner can read a glyph. Where are the glyphs on this?
They're on the bottom of the chess pieces.
Oh, okay. Now you've got this set up. The last time I messed up your problem. I'm not going to mess up your problem here, but here's a queen. Now I know it's a queen because I can see it looks like in the newspaper when you see a chess position.
Right.
But the computer's not looking at the queen's head, right?
That's right. It's just reading the data that's embedded in the marks.
Can't be much because a queen, it just says this is a black queen, right?
It's just positional data. There's about 20 bits.
Okay. Can this be a fairly rich form of data storage?
We can store about, depending on the print resolution, your scanner resolution, we can store several hundred bytes per square inch. About
Really?
300 or 400.
Well, quite a bit.
Yeah, that's right.
Oh, that's amazing. All right. So the scanner is going to get an image of the bottom of the pieces.
Right.
And then what happens?
Then it's going to figure out where those pieces are, what they are, and feed that information into a chess program.
So you're using Crafty, which is a Unix-based chess program, but you could use any chess program that could communicate, right?
That's right.
All right. Well, let's go. So let's see the position. Let's see if the computer can tell.
Okay.
It actually is going to solve this. This is a chess problem. If you want to play at home, folks, white to play and mate in 3.
All right. First, we'll show the board position.
Okay. There you go. And again, we're not doing this because it's the fastest and easiest way to do it. We're doing it as a demonstration of glyphs, right?
That's right.
And there, look, you got the board position. It came out. It got it exactly right. Does it ever make a mistake? I mean, this is a pretty reliable technology. Yeah.
Well, when we first started, it made lots of mistakes. That's why this is a testing platform.
It works pretty well. How does it looking at the grid, how does it know where the pieces? I know it knows what the pieces are. How does it know where the pieces are on the?
Actually, there's a registration pattern under this card.
Oh, this is a little glyph here.
Right, this is a data glyph.
Okay.
So we get all the positional information of where this pattern is, and then we can say, oh, well, this square is an inch above, another inch above.
Got it. So it's ignoring the grid. That's just for humans?
Grid is just for humans.
All right. Hey, just out of curiosity, how do you solve that problem? I'm curious.
All right, let's solve this guy.
Let's see if Crafty can figure it out.
Okay.
We're going to do this by command line. Make play. Then we'll go back over and Crafty. Oh, the check. See, I wasn't looking at the check. So knight takes pawn. I kind of looked at that briefly. Knight takes pawn, check, and then king goes over there to g1, and then I don't know what else happens. Okay. That's very cool. And it solved that, and it did it all from there. Now, another advantage you said of glyphs is that they're reliable.
They are.
You have some examples of this is a piece of paper with some text on it. This data is encoded in here as a glyph.
That's right.
Now, I guess when you burn a hole in the paper, you can't read what's under there. But when you burn a hole in the glyph, can you still read it?
We can get the information out, no problem.
So all the data is still stored here?
Everything, the fonts, the text.
Really?
The image of that page is stored in the data glyph.
I noticed this is, I mean, it's not human readable, really. It's so fine. So that means you have a lot of data density there, right?
Most of it's error correction, actually. There's a lot of data and a lot of error correction.
And that's why a hole isn't going to make a difference. Are you using parity or something more sophisticated than that?
We're using Reed-Solomon error correction.
Okay.
It's based on Galois
sure.
theory.
Okay. So that really is a very good error. It's not merely that you've got 15 copies of that page printed over there.
A little more
sophisticated. More sophisticated than that. Coffee stains, same thing?
Actually, the coffee stains are even easier because we can still see the marks, the forward and back. We read right through
it. The color doesn't bother it.
No,
That's
no
pretty
problem.
amazing. What kind of applications do you see for these glyphs? Oh, that was my shirt. But it's a glyph, too. Many people don't know that. Actually, we can interpret this shirt. I'll tell you what. We've got this. I've taken the pattern of my shirt, and I've put it here on the screen. You see that? And if you want to play with this, it's kind of fun. If you go to the part, you can decode glyphs on here. So let's decode this secret data glyph and just see what it says. It's going to take a. Well, no, that's not right. Leo's hair is not real. Ken, you didn't tell me that's what the shirt said. Oh, my goodness. That's fun. What kind of applications for the future?
There's lots. There's document security. There's paper user interfaces.
U.S. government could use this on money.
You can imagine it going on documents that you care about, like financial documents. That's exactly right.
Yeah. Very cool. Hey, thank you so much for coming in and demonstrating. This is a neat project. Jeff Breidenbach is a researcher at the PARC. No longer Xerox PARC, just PARC. For more information on how data glyphs work well, as well as some secret messages we've hidden in our own data glyphs, check out the website of the Screensavers.